Hi friends, good morning to one and all and my respected teachers. Today am I like to tell about solutions to matrix equation and its application in controls. Myself, DLN Sai Jishnu from CSC Data Science B section. The next slide is contents. In this PPT we are discussing about introduction, mathematical model, linear systems, closed form solutions, eigen and eigenfunctions, Newton method. The next slide, introduction. The linear matrix equation often appeared in applied mathematics, physics, and the system of and control theory. For example, the dynamically linear model x comma x into t plus ax t is equals to bu t can describe many practical systems in engineering where vectors and are the state vectors or the control vectors and are the system coefficient matrices. The theory model above is finally to study and solve generalized Sylvester matrix equation. Xb minus Ax is equals to Cy. With unknown matrices, this matrix equation has important application in the eigenvalue assignment observed designer, eigenstructure assignment design, and constrained control of the above linear system to solve the quadratic eigenvalue problem. Delta square ax plus delta bx plus cx is equals to 0. Each step of Newton's method needs the solution of generalized Sylvester matrix equation. The literature on the explicit solution of linear matrix equation is large and still growing rapidly. In parametric solution, expression to generalized Sylvester matrix equation is Ax minus Exb is equals to Cy. These are the two equations that generalized Sylvester matrix is used or introduced. The next slide we are talking about mathematical model. First of all, what is mathematical model? Mathematical model is the process of describing a real world problem in mathematical terms, usually in the form of equations, and then using these equations both to help understand the original problem and also to discover new features about the problem. Present, the result in is that all. It is a bridge between real world and mathematics. How mathematical model is helpful and ways to define mathematical model. Mathematical model can take many forms including dynamical systems, statical models, differential equations, or game theoretic models. These and other types of model can overlap with a given model involving a variety of abstract structures. In general, mathematical models may include logical models. In many cases, the quality of scientific field depends on how well the mathematical models developed on the theoretical side agree with results of repeatable experiments. Lack of agreement between theoretical mathematical models and experiential measurements often leads to important advances as better theories are developed. In this slide, we are discussed and known about mathematical model. The next slide is also we in this slide, in previous slide we discussed about definition, how mathematical model is useful, what is mathematical model. But in this slide, we will know about the Examples and conditions of the mathematical model. In the physical science, a traditional mathematical model contains most of the following elements: governing equations, supplementary submodels defining equations, constitutive equations, assumptions and constraints, initial and boundary conditions, classical constant and kinematic equation can understood. It is a bridge between the real world and mathematics. So the why we say the bridge is it is most important to the I mean the real world and mathematics. Example: an ice cream company keeps track of how many ice creams get sold on different days. By comparing this to weather on each day, that they can make mathematical model of sales versus weather. They can then predict future sales based on weather forecast and decide how many ice creams they need to make. In previous slide, we discussed about the mathematical model. In this slide, we are discussing about linear systems. First of all, what is linear system? In systems theory, a linear system is a mathematical model of a system based on the use of linear operator. Linear systems typically exhibits features and properties that are much simpler than the non-linear case. As a mathematical abstraction of or idealization, linear systems find important applications in automatic control theory, signal processing, and telecommunications. For example, the propagation medium of wireless communication systems can often be modeled by linear systems. Definition: the definition of linear systems is a general deterministic system can be described by an operator H that maps an input xt as function of t to an output yt, a type of black box description. A system is linear if and only if satisfies the superposition principle or equivalently both additively and homogeneity properties without restrictions, that is, for all inputs, all scaling constants, and all time. The superposition principle means that a linear combination of inputs to the system produces a linear combination of the individual zero state outputs, that is, outputs setting in the initial conditions to zero, corresponding to the individual outputs inputs. In this system that satisfies the homogeneity property, scaling the input always resulting in scaling the state response by the same factor. In a system that satisfies the additivity property, adding two equations always resulting in adding the corresponding two zero state responses due to the individual inputs. The next slide. Mathematically, for continuous time systems given two arbitrary inputs x1 comma x2 as well as their respective zero state outputs, y1 is equals to h of x1 of t, y2 is equals to h of x2 comma t. Then linear system must satisfy this equation is most important of the linear equation of linear systems. This is a general representation, I think. A y1 of t is equals to b y2 of t is equals to h of ax1 of t plus b of x2 comma t for any scalar values alpha and beta for any input signals x1 of t and x2 of t and all for all time t. The system is defined by the equation h of xt is equals to y of t, where y of t is some arbitrary function of time, and x of t is the system state. Given yt and h, the system can be solved for x of t. The next slide is. In this slide, we are discussing about closed form solutions. An equation is said to be closed form solutions if it solves a given problem in terms of functions and mathematical operations from a given generally accepted set. For example, an infinite sum would generally not be considered closed form. However, the choice of what to call closed form and what not is rather arbitrary, since a new closed form function could simply be defined in terms of infinite sum. It is worth noting that the adjective closed is used to describe a number of mathematical notations. Example, the notion of closed form, loosely speaking. A discrete function is of a closed form if it shares certain essential properties with the hypergeometric function, a function which itself is defined to be a solution of the so-called hypergeometric differential equation. This particular notion of closedness is completely separate from the notion of closed form expression as discussed above. In the particular, the hypergeometric function is considered a special function and is not expressible in terms of operating which are typically viewed as elementary. What's more, certain agreed upon truths like the insolvability of the quintic fail to be true if one extends consideration to a class of function which includes the hypergeometric function, a result due to claim. In this slide, we are going to discuss about eigenvalues and eigenvectors. In linear algebra, an eigenvector or a characteristic vector of a linear transformation is a non-zero vector that changes at most by scalar factor when that linear transformation is applied to it. The corresponding eigenvalue, often denoted by lambda, is the factor by which the eigenvector is scaled. Geometrically, an eigenvector corresponding to a real non-zero eigenvalue points in a direction in which it is stretched by the transformation, and eigenvalue is factored by which it is stretched. If the eigenvalue is negative, the direction of reverse, loosely speaking, in multidimensional vector space, the eigenvector is not rotated. Formal definition: if T is a linear transformation from a vector space V over a field F into itself and V is a non-zero vector in V, then V is an eigenvector of T. If T of V is a scalar multiple of V, excuse me, it is a equivalent to define eigenvalues and eigenvectors using either the language of matrix or the language of linear transformations. If V is finite dimensional, the above equation is equivalent to, where A is the matrix representation of T and U is the coordinate vector of V. T of V is equals to lambda V, A of U is equals to lambda U. From that equation, A minus lambda of U is equals to 0. This is the equation for eigenvectors and eigenvalues. There is a matrix example of two-dimensional matrix. Consider a matrix is A is equals to 2, 1, 1, comma 2. The eigenvectors of V of this transformation satisfy equation 1 and the values of lambda for which the determinant of matrix A minus lambda I equals to 0 are the eigenvalues. Taking the determinant to find characteristics polynomial of A minus lambda A is equals to 2, 1, comma, given matrix minus lambda into I, that is equals to 2 minus lambda, comma, 1, 1, 2 minus lambda. By simplifying it, by determining it, 3 minus 4 lambda plus 4 plus lambda square is the given answer, and the roots are lambda minus 3 is equals to 3 comma 1. Setting the characteristic polynomials equals to 0, it has roots at lambda is equals to 1 and lambda is equals to 3, which are the two eigenvalues of A. For lambda is equals to 1, the equation becomes A minus 2I, lambda is equals to lambda equals to 1, so A minus I is equals to 0. From simplifying the equation, a non-zero vector with v comma 1 is equals to v of 2 solves this equation. Therefore, uh, v is equals to the eigenvectors are 1 comma minus 1 is an eigenvector of A corresponding to lambda 1 as in any scalar multiple of this vector. When you put lambda is equals to 3, equation 2 becomes any non-zero vector with v1 is equals to v2 solve the equation. Therefore, when lambda is equals to 3, v1 comma v1 is equals to 1 comma 1 is an eigenvector of corresponding to lambda is 3 is an any scalar multiple of this vector. Thus, the vectors v lambda is equals to 1, v lambda is equals to 3 are eigenvectors of associative with eigenvalues lambda is equals to 1 and lambda is equals to 3 respectively. This is the eigenvalues and eigenvectors example. Now we will go to Newton's method. In numerical analysis, Newton method, also known as Newton-Raphson method, named after Isaac Newton and Joseph Raphson, is a root finding algorithm which produce successfully better approximations to the roots of a real valued function. The most basic version starts with a single variable function f defined for a real variable x. The function's derivative f and an initial guess x comma o for a root if the function satisfies sufficient assumptions and the initial guess in close, then x1 is equals to x naught minus f comma x naught by f dash comma x naught is a better approximation of the root than xo. Geometrically, x1 comma 0 is the intersection of the x axis and the tangent of the graph at f. That is, improved guess is the unique root of the linear approximation in initial point. The process is repeated as x comma xn plus 1 is equals to xn minus f of xn by f dash of xn until a sufficiently precise value is reached. The algorithm of the first in the class householder method succeed by Halley's method. The method is also can be extended to complex functions and system of equations. The conclusion of these solutions of matrix is it is well known that the matrix equation plays an important role in stability analysis and controller design in linear system. In this article, we develop a Smith normal form reduction for computing the solution to pair x comma non-homogeneous matrix equation xb minus ax plus is equals to cy plus r. The closed form solution to the non-homogeneous matrix equation are presented. Finally, numerically applied examples is provided to support the theoretical findings and to testify the effectiveness and usefulness of the developed algorithm. Thank you for giving this golden opportunity. Thanks. Hope you guys liked my PPT.